thank you for attending this webinar. Like I was mentioning in the beginning, today we're doing something a little bit different in that we're also hosting a live training in Minnesota. And so this is going to be part of that training, and but you'll have access to this webinar after the fact. So my name is Carlos. I'll be presenting today, and today I'm also being joined by Andy Leonard. He's one of our senior applications engineer out of our Novi office in Michigan. And we're also joined by Christoph Blumenthal. He is a North American product sales manager for Zeiss Quality. So with that, let's go ahead and take a look at the agenda for today. So first, we're going to highlight a few characteristics that are important for material quality and why it's important to take advantage of all that data that is available. We're also going to be talking about how traditional methods may leave some room for opportunity and what some of those real world applications are, and some of the features that the Aramis system fulfills. We're going to go into a little bit of an introduction to the Zeiss Quality Suite, more specifically the Zeiss Inspect overlay. We'll do a little bit of demonstration. We'll go into batch processing and using kiosk mode and a few other areas of opportunity that'll make testing a lot easier. And then we'll go through an overview of how easy it is to actually set up the optical testing with the Aramis system, how you can leverage us, and then we'll go through a case study that will ultimately provide the value that a system like the Aramis system is going to provide for our partners. We'll also have a section for a Q&A. And again, if you're attending this webinar, questions pop up, please include those questions in the Q&A section for the webinar, not the chat box. It just makes it easier to track and go back to the actual answers. And then we'll go into how to get started, right? And some of the conclusions that we reached today. So with that, why is material quality so important? I think a lot of folks are familiar with this image. All in all, it was a series of compounding effects, right? Everybody thought it was just due to a leak. For a long time, there was a story that maybe it was the paint that was actually flammable. But the reason why I brought this up was that it depicts very well how things can go wrong if you don't understand all the qualities that are going to play once it goes into a real world application. So what are some of those qualities? So I think everybody attending this webinar, everybody here in this training room, they're very familiar with strength, durability, cost effectiveness. That is also usually one of the primary motivating factors to conduct a lot of the testing that we're performing today. But at the same time, we also need to fulfill certain maintenance requirements. We also need to keep in mind how sustainable some of these materials are, some of the aesthetics. And so as we go through, and I like to start with this image, if only because for a long time when we were analyzing the concrete that was being used in Roman times, everybody always thought that there were some defects in how they were mixing cement. Lo and behold, as we started examining those qualities a little bit more, we found out that this cement was actually, or this concrete rather, was actually self-healing. So all of those defects that we noted in the beginning, they were actually features that help that concrete withstand the test of time. And as I understand it now, these are areas of opportunity where folks are starting to use it in current implementations of concrete. But at the same time, material quality also surfaces needs that we may have depending on the application. So what I'm showing right now, it's the NASA Alloy GRX 810. For one, I'm partial because we work very closely with NASA Glenn. But this material in particular, it was developed to withstand certain temperature requirements as part of a 3D printing process. And so now we have the ability to create something that has never been created before because we went back and took a look at the material qualities that we needed to fulfill. This is also going to open up the door for basically withstand higher temperatures and lead new areas of opportunity and innovation. So when it comes to Why is it important to innovate? Why is it important to understand these material qualities at beyond just the surface level? I think gigacastings in general are a new application that we are starting to see throughout the automotive industry. But you see this in tons and tons of different processes throughout different industries where the new technology that we have access to is allowing us to create things that were never created before, because now we have different ways of understanding how those materials behave under certain conditions. And that's exactly what was happening with these gigacastings, right? So as we start developing more components on a greater level, we can analyze them more wholeheartedly, how they interact within the system itself, and treat it as a system and not just a component. We have some links. We can make all of these available to you after the fact. But again, this was a great use case that highlighted how we are using the technology today. And I wanted to close this section with this slide in particular, right? Many of life's failures are people who did not realize how close they were to success when they gave up. This is why we're here, right? Oftentimes, we test certain things to a certain degree, um, and understanding their value is a product of all the efforts that go into going through all of those processes and understanding how these material qualities affect the final product. So with that, we'll go into discerning a little bit more of the traditional testing methods and some of the areas of opportunity. I think you'll be very familiar with many of these if you've spoken with us in the past. I'm sure you have seen this slide, but essentially we already have a number of different mechanical point solutions that allow us to see data in a certain way, right? And we can encompass them into this neat little box that we call single point mechanical solutions to understand displacements, vibrations, strains. And this methodology in general, it's great. It provides great data. There's a large volume of folks that know how to use it. However, with the new models that are being created, they're becoming more complex than ever before. They require more data, and they're being used more throughout every single industry. So once we start taking some of that data from the single point mechanical solutions, we start understanding that there are certain gaps that we need to fulfill. Um, I think one of the biggest challenges that we have with single point mechanical solutions is the fact that they only give you one specific data point. And these models require more data than ever before. And so if you want to go through a cycle or a process to create a good model that is more complex than ever before, and you want to also feed it good, relevant, real-world data, there's going to be a certain amount of time that goes between those tests. And so as more things are being asked of us, the testing community, to provide better data at better times, that's one of the areas of opportunity that we wanted to highlight in the webinar today, and how the Aramis system is able to give you that data from a full field perspective. So as opposed to a single point mechanical solution that gives you a very specific data point, the Aramis system would be able to give you that data on thousands of points. So we'll go through some of the benefits of using a system like this. But in essence, it gives you a better access to feed these models and implement more quickly. So what is the Aramis system? If you're not familiar with it, this is a very simple representation. It operates very much like our pair of eyes. It's a stereo camera pair that is able to hone in on a point down to a 50th of a pixel to be able to track displacements. In this first example, we're using that dot and we're placing it on this test to be able to track the displacement as the person is walking. Now, if you were part of this test, you know that setting up all the additional sensors to get this type of data would probably take a long time. Whereas with the Aramis system, as long as you can place those target dots, the system automatically recognizes those target dots and then tracks the displacement for it. At the same time, we can create a stochastic pattern. So I think a lot of folks are very familiar with material samples. And so if we can create a stochastic pattern on a material sample, now you're able to get thousands of points across the sample and then track those thousands of points that will give you a better idea of the data that you're able to get, all the way down to the Luther's bands that you can see here developing as the material is being stretched out. So with that, we want to highlight this video. I think it gives you a really good idea of some of the applications that you can take and use Zeiss Inspect Correlate. Mm-hmm. What's that? Oh, yeah. And with that, we'll go into the actual automating, testing, the data analysis that we spoke about. So this is very similar to the slide that we had already covered, where in essence, we're just highlighting some of the different tests that are available to you when you're performing, for instance, tensile tests. You can use extensometers, clip gauges, video and laser extensometers. But the value that a system like the Aramis provides is that it's an all-encompassing solution. So in this video, you can see, similar to the one before, you're getting these thousands of points through a series of images that you can build into a video. At the same time, you can feed it into some of the processes that you're already taking on and integrate it. So you can import data from the load frame, for instance, so you can understand load displacement to enhance some of those analysis capabilities. You can also automate it, which means you can output things like the stress, the strain curve, and you can input you can input some of the data for the material and create these reports automatically. And then finally, you can customize how the outputs and how you're performing some of this analysis. Again, this is just a little bit more of that, where we're showing the yield curve comparison for different reference lengths. Go through one of the areas that I think we are very familiar with is how sometimes when we use clip gauges or things of that nature, they may pose a challenge to the data that you're actually collecting. And so with a system like the Aramis, you can still use some of those clip gauges, but you can also identify where some of those clip gauges may be affecting the data that you're getting. And because it's a full field measurement, you'll be able to record that and make sure that you're accounting for some of those artifacts that are being created. Another area of opportunity that we've identified with the Aramis system is the fact that now you can take a look at, for instance, polymers where you're experiencing 1,000% strain. Because it's that full field measurement, as long as you can see the specimen, you'll be able to quantify that data across the spectrum of the image that you're collecting. And with that, we'll go into a live demonstration of Zeiss Inspect Correlate. So I'll stop sharing my screen.
Hello all, this is Andy Leonard. Thank you for bearing with us as we switched over machines. And yeah, I am one of the applications engineers out of Trillian's Novi office, and I am very excited to share with you one of the Zeiss Inspect Correlate's very powerful features, the automated tensile testing script. And keep in mind, we do have versions of this tensile testing suite that are even more automated When we have the live feedback of a universal testing machine with the live force input, we can run very many samples in a row at operator level interaction and automated reporting. With the pencil testing script, though, we can come back and reanalyze or analyze data just as long as we have the 3D image series of the tensile pull and a force channel as we do in this project. So it's a two-step process. The first step is to run the preparation script. So under add-ons, we'll go to execute script, testing, and tensile test preparation. And this will generate a surface component for us. We can click OK. And this is going to run through and crunch through all of the images, making sure that the surface component is computed in each. So for the folks in the classroom with me today, as I was saying earlier, this is that way of getting the automated coordinate system without having to set the 3-2-1 alignment ourselves. So very, very handy for material testing. And with that all being finished, we can see our coordinate system has been placed in the bottom left of the tensile specimen. And we'll start the second step of our two-step process: execute script, testing, tensile test, evaluation. And within this window, we can customize what exactly it is we're looking for. If we're looking to perform a test to ASTM standards, for instance, we have those populated. If we're testing plastics, we can test to ASTM D638, or we can input custom values if we have, if we want to kind of customize what we're looking for. We'll stick with the defaults for now. I believe my specimen width was 18 millimeters in this case, but we'll leave the rest of this the same. We'll click OK. And now the software will crunch through and generate a full material report for us. Keep in mind too, as this goes through, I'm working on my office productivity laptop. Typically with the systems that we would employ in the field for actual acquisition and analysis, this process would happen even faster. All right, and there we are. We see we've got our full list of material parameters that we were looking for. I believe it's epsilon y, or strain in the y direction, that's plotted in the image view for us. And if we want to take a look at the report, we can jump over to the report workspace to view the stress strain curve, end value fits, along with a fully customizable suite of whatever materials properties you happen to be looking for. Yeah, awesome. Thank you very much. And we'll toss it back over to Carlos.
You can stay connected and just...
In this video, it'll go through a series of interactions that are very similar to what Andy was covering. But in essence, you're pressing a button. The material's already been prepared. And so the system's going to pull in a lot of the information from the load frame and perform all of those tests that we need to acquire. Because we already have basically the question marks for the data points that we're trying to solve for. The system is going to script a lot of the data capture. So once it goes to the full test, then it will start adding them into the project that we created in Zeiss Inspect Correlate. As you can see, that video basically closes out with generating those report pages that you can now share internally, do with as you'd like. To take this a step further, what we started doing here at Trillion is we have a system of processes that we can automate to take the kiosk even farther than what we just showed. And basically this code, it's very simply creating a series of reports, a series of investigations into the material qualities. We're also pointing the software to the different areas where it's gathering the data from. And we're pointing it in a direction where we can start looking for the values that are being created into a CSV file. Again, super simple, but at the same time, this can be customized to your heart's content, meaning as you start creating more complex projects, as you start going through a series of implementations where you're testing out 100, 200 samples, 300 samples, this becomes super powerful because now while you have your operators creating these tests and going through the data acquisition, you can then have an analysis team that is going through the full data that you just captured. And so the process itself becomes a lot more powerful because now you're not being held back to that headcount that is able to perform the analysis. And again, this is just another example of how we can take something super simple like this code and start gathering some of that data. So with that, we'll go into how you would implement the Aramis system. First of all, we'll highlight some of the benefits, I guess, that we just covered. And in essence, it's a non-contact method of acquiring data. There's no need to necessarily reset like you would using a strain gauge or something of that nature. You can continue testing with all the methodology that you already have, but at the same time, it's independent of the length of that strain gauge. It's very accurate to high strains as well as variable rates for accurate measurements. You can start measuring local effects that would normally go unnoticed with traditional testing methods. And you can also identify different issues that may arise from using some of those single point mechanical solutions. You can, once in full implementation, you can automate a lot of the workflows that you're already performing. And you can create this kiosk mode that is very specific to your use case that will allow you to go through a lot more of those material testing samples. I guess this is more of a something to be aware of if you do want to use visual image correlation and you're satisfied with some of the results that you're getting from like a 2D system, just be mindful that sometimes you are going to go through different areas that may not be readily apparent. So when you're using a 2D contact measurement system, because you're not accounting for that z-axis, that may also play a role with some of the data that you're going to be capturing. So like it's highlighting here, right? So the movement of the camera and the tripod in relation to the sample, whether the sample itself is tilted, whether you have certain areas that are within the field of view, or there's certain areas that may be bulging, or may be a factor of the lens itself that you're using within the camera. Here we have just an example of comparing the 2D measuring data to a calibrated 2D measuring data and how that compares to the 3D measuring data. As you can see, obviously the 3D camera is going to be a lot more accurate. But as you continue with the testing, you can see how much it can deviate depending on what area you are looking at. And again, this is just another chart depicting the differences between that 2D system data as opposed to the 3D system data. And again, just to recap, some of the benefits of a system like the Aramis system: it's non-contact, it's full field, it's all in one. It's very flexible and it's independent of different material qualities that you have. And finally, and I think this is probably the most powerful, it's the fact that it's designed to adapt to different evolving needs of the organization. So as you start creating some of those fancy new materials that you're looking to implement, it's a lot easier to use that tool set that you're already familiar with and then adapt the system like the Aramis system to continue testing and make sure that you're not wasting a lot of time implementing different test designs. And finally, it's able to interact with a lot of the machines that you're already capturing. The fact that it's so well integrated into the Zeiss Qualities suite, it means that a lot of that data is equally applicable to different use cases. And so it's creating more of that environment that you don't have to leave the system to perform some of the analysis that you're already performing. And really the applications are endless, right? If you can see it, you can measure it. You can go as simple as a 2D elongation study all the way down to analyzing different more complex material qualities like bulge tests or shear tests, or even dropping a helicopter and performing a strain analysis on how it behaves. And then this section, basically, we just want to let you know, right, we are here as your partners. We are here as service providers. We are the experts. We've been in the industry for 25 plus years. And so we are where you are. We're always traveling. We're always meeting with customers. We have offices in both ends of the country. And we can perform a lot of this analysis even as a service so that you don't have to start looking into how you're going to implement a system like this. And you can let us start creating some of those proof of concepts so that you can start developing that data, or you can start gathering that data without the need to understand necessarily how to use the system. And then as you start getting some of that data and you start seeing the value of the data, that's where we can come in and basically help you get into a system that fulfills the needs of the organization, not just for today or tomorrow, but we also help you look out into that longer term 5-year implementation, how the organization is growing. So all of those kiosk implementations that we talked about, all of those batch scripts that we started talking about, these are some of the implementations that we have taken on with customers. These were to fulfill a certain quality that they needed out of the software. And so we're providing that service to those customers and then making those available to the additional customers that we have throughout the country. Just a brief overview, right? We work basically everyone out there, everything from automotive, where I am, aerospace, consumer goods, material suppliers. So we have a lot of experience in different areas. And with that, we'll take
Yeah, thank you everyone for inviting me to this. So my name is Christoph Lumthal. I'm from Zeiss in Germany, and I'm happy to be here today. And I would like to give you a case study of the implementation of the Aramis kiosk mode for material testing. And I will do this by going into this project that you can see on the screen, characterization of carbon fiber composites using Aramis kiosk. This was an implementation by BMW in Munich in Germany back in 2017. So it's not the very up-to-date project, but I still think it showcases strengths of the kiosk mode really good. And I Yeah, I hope you enjoy it. So this presentation is actually done by BMW, and I'm happy to repeat the same slides, of course, with their permission. The presentation is basically structured in two parts. The first part is can be seen as a feasibility study, and the second part is the actual implementation. The components or the materials that this is considering is used for the model i8, and so this is an electric vehicle and lightweight is crucial. So they are going for carbon fiber materials, and of course those materials are requiring constant testing, material testing in different ways: tension, compression, shear, 3-point bending, 4-point bending, and so on. And the purpose is most of all to fill a material card and a material database for the right material selection then in the design phase. The specific project that this is going a little bit deeper is a compression test. This is a long specimen, but it actually has a 10 millimeter by 10 millimeter of focus deformation zone inside the test machine that we want to view with DIC. And you can now see on the right side picture that this is a little bit challenging for the optical accessibility, but it's not a problem. I will come back to that in a second. The state of the art measurement so far is a strain gauge. So that means a single strain gauge on this coupon, which is implemented horizontally. So that means like the strain in X while the compression comes down. So, and you can see there's a failure of this strain gauge at very low strains. Of course, this is an integral strain, so an average strain, and certain fibers, so areas have higher strain, but the stress strain curve is failing kind of early. For this feasibility study, a 2D camera, 2D setup, a single camera was selected. So first of all, this was a bit easier to achieve for the engineers. As I said, they were worried about the optical accessibility, but also the 2D DIC software, the size and spec correlate for 2D is free, so this is also a very low problem to jump over. And in the feasibility study, they covered also two setups: the front view of the specimen and the side view. You can see here again how little really the interested zone is. So this is the pictures of the side and front view with the DIC pattern. And this is the results of the side view. And you can see the two different results they use. They first use an extensometer, but also the local strain distribution. And they found the local strains really useful for understanding more the failures of the first failures of the 3 layers. And the actual buckling, for example, that takes place here. So far now in 2D, they can only assume that there is buckling, but they will go to 3D and confirm that there is. But they also use the 2-point extensometer because they find that even though there is delamination, the coupon as a whole still has a certain strength, and they want to also acknowledge for that. And so with this extensometer evaluation, they can go feed this to the stress strain curve, and they get values to much higher strains. Even though, of course, in the stress strain representation, there is certain fibers already broken. Yeah, I think I covered what is this slide about. Yeah, and so this is basically the first part. The feasibility has been done. And now BMW wants to implement this in their test lab as as a standard setup. And so they have requirements that many of you may know, and that are not so much on a technical or on a scientific level, but they require a stable running system. They require a sturdy setup. A 3D setup for the buckling that I said. But you can see also here the operating should be done for multiple level of education, study backgrounds. Many users should be able to perform those tests. Not everyone should be a power user of the RMS system. And this is where the kiosk mode actually comes into play. The kiosk mode is a reduced surface of the RMS Professional that only gives you a very limited amount of buttons to click. So you don't have to be an expert, but it also, the whole setup they choose makes the whole workflow a lot quicker and user independent and reliable and repeatable and so on. So it's really an industrial setup that they have achieved here. This is a picture from the setup, and they are using a Zwick machine, and they also, of course, are combining the Zwick or the test machine computer with the GOM computer that controls the RMS system. Before we go further into this, I want to also point out that they have mechanically done a very sturdy fixation of the system next to the machine. So this is not a tripod setup, but there's basically no way that someone can, by mistake, displace the sensor. It is mounted fixed. Yeah. So this image here showcases that they combine the control of the test machine with the control of the RMS. So whenever the test starts, RMS gets a trigger and also starts recording, and when the test is done, when the samples break, the acquisition also ends. And there's even the possibility to give more triggers, like when going through different phases or reaching different load stages. In this case, they have done kind of a, let's say, semi-manual or semi-automated way of saving all the strain results. So they have had a script that saves the strain exports to a common Zwick interface here and gives us to a database basically. But at the time now we have also other methods for synchronizing the RMS with test machines. For example, the Skippy live feed. This is, for example, the Skippy live feed is implemented by MTS, but also by HBM for data loggers. And I think this is even a further implementation than the saving of strain documentation as they did here. And so the actual procedure of running a test in the kiosk mode looks like this. By the way, you've just seen the kiosk mode in the video that Carlos had run. Now we start with a screenshot number 1. We give the test a name, or the number or specimen a name. Maybe we manually have to enter the thickness or some other data to the project. But then we go to stage 2, and as I said, it automatically starts recording with the test machine and stops the recording with the test machine. After that, it goes to the calculating the results, like stress strain curve and other fitting curves, This is in screen 3, where the user can still do some inputs like changing maybe the limits of the elastic phase or whatsoever if he chooses to, but you can just click OK and then you end up with the reporting. This is a screenshot number 4, reporting and exporting of data. After that, you just hit next test. For this kind of runs, that you can implement different kind of templates. So if like BMW here has different kind of tests, tensile tests, compression tests, and more, you can have different templates and each different test is then run with a different template. So not so much effort for the user in the end. Yeah. And this is basically the conclusion. The BMW says they have a stable running system with automated start and stop. They can perform various tests with simple graphic user interface for the end user. It is a sturdy setup that doesn't get interrupted. And a 3D camera that gives 3D data, but also requires very little recalibration. Yeah. So, and I'm not 100% sure how much data they, or how many specimens they test, but it was stated that they test multiple series a day. And I know that it's since the implementation 2017 still in use, that I think is a good point alone.
Excellent. Thank you.
Thank you.
All right, guys. Yeah, so I think one of my favorite ideas to take away from that case study is the fact that you can automate so much of that testing. As glamorous as testing can be, we always want new components or new ideas, right? One of the realities is that oftentimes that testing is very tedious, especially if you do have to characterize thousands and thousands of samples. And that's where automating, even beyond that kiosk mode, is where it becomes really powerful. So with that, we can go through a little bit of the Q&A. So the first question is, what is your range of specimen and structure sizes? Basically, it's whatever the system can see. I don't know if, Andy, you have a different point of view or something a little bit more intelligent to say than me, is whatever the camera can see, right? But that's about as simply as I can answer that question. Because it is so dynamic, depending on the different fields of view that the camera has, that's kind of how I would answer that question.
Yeah, no, that's absolutely a great way of answering it, Carlos. With Aramis digital image correlation, we are able to measure quite a wide variety of sizes, from millimeters all the way up to the scale of meters. So it really does depend on the application. And we, as far as setting up goes, we have various tools and resources that can help our users decide what size is best for them given the equipment that they have. The Aramis app on the Apple App Store or the Google Play Store will help you size your measuring volume appropriately.
Cool. And can we talk about more of the video extensometer capabilities?
Yeah, although it's much more than a video extensometer, we can use the Aramis cameras for video extensometer capabilities in a number of different ways, whether that's just creating simple two-point distances, using the pattern matching algorithm to track just 2 points, and we can define these any way we want to a certain gauge length or extensometers of various sizes all over the specimens to look at local and non-local deformations.
Got it. And then do you have some examples of implementing the automation of materials testing and processing data in your website? If you want to reach out, I can certainly send you the links, see what we have readily available. I can also connect with you one-on-one and see what would make the most sense. Basically, the main reason why I answer that way is that oftentimes, especially with a kiosk implementation, I think everyone's situation is ultimately a little bit more nuanced. So once you set it up, it's great to up and run, right? But it may not be relevant to your specific use case. But if you'd like to connect, like I said, we can certainly talk about it. What else? How fast can we record? Basically, depending on the system and depending on how we are using it, with the Aramis system right off the bat, I think with the 24M, we're just kind of going through that, right? It can go all the way up to like 300 hertz. But then you can also use high-speed cameras and export some of those images. So basically, to answer that question, the most broadly way possible is as fast as you need to go. Depending on the implementation, right, it's going to take a little bit more of a conversation, but I think that's never stopped us from testing something essentially. Then what is the calibration process like? Andy?
Yeah, absolutely. If you can turn on your video real quick. Luckily, I have a calibration object right next to you. So for the calibration process, we'll take between 10 to 20 images of an object that looks kind of like this. We have the auto blur kind of working against us here, but there's a grid of points that the software will see. And we'll take multiple different images of this object at different spaces, different orientations, and the software will build the calibration based on the combination of left and right camera images of that.
Cool. I think that's it. Any questions from the room?
Yes.
Repeat that question.
Yeah, so we have somebody in the room that asked whether the kiosk mode is implemented through scripting or how we actually go about implementing kiosk mode.
Yeah, and absolutely. It's through Python scripting, as well as templates created through the Zeiss Inspect ecosystem, but mostly the Python scripting.
Do you have a problem with storage, just if you're doing a kiosk with a lot of throughput and raw samples?
Mm-hmm. Yeah, the question was data storage considerations and how that all kind of adds up depending on camera resolution, number of pictures taken. Project files can quickly add up to gigabytes. So there's a number of different ways that we have available to us to manage project size. It's become quite easy in recent years. We can mask off images to reduce unused areas, or we can, once we're fully done with the analysis, if we just need to save the project for traceability purposes, we can permanently reduce the resolution of the images in the project, which frees up quite a bit of space.
Anybody else? Yes.
Yeah, I believe so. I believe we will be sending up follow-up emails with contact information. If you want to get in touch with Carlos or Christoph, or for some reason me, we can send all that out.
So do you have tough time matching up the timestamps between, say, a controller and your system, like the timestamps?
No, the question was about synchronicity between third-party devices and our controller. If there's any difficulty matching up the timestamps of them, and as long as we have analog signals fed into the Aramis controller, they're the data capture is essentially simultaneous. Yeah.
I think the term is automatically.
Automatically. Yeah, there you go.
It's a technical term. Cool. And I think that pretty much wraps it up for us. Like I said, we'll be following up with a recording of this webinar. You can also reach us at any time and chat a little bit more about the implementation, what that would look like. And we can talk more specifically about the use case and some of the value drivers for you to make sure that whatever we're talking about is specifically that. It's a value driver for you. And with that, we'll close it out. Thanks, everyone.
Thank you so much.